So we were looking at spectral methods in the last class, and in particular we were looking at PCA. And what we found was very simple computations based on eigen decomposition can help you do dimensionality reduction, can help you separate signal from noise. And I think in the recitation, was it Guanya who covered it? So you probably got like the other methods as well, right? Like other dimensionality reduction methods based on eigen decomposition. So you saw that there's many variants, whether it's unsupervised versus supervised, right? Or it's multiple data sets, you want to look at the correlation between them, but in a canonical basis. So all these are variants of PCA, right? So PCA is the simplest one, and then there are many variants. And the beauty of it is if you're looking at a Gaussian-like model or Gaussian assumption, right, that's implicit when you look at covariance matrices, you can solve these problems optimally, right? So that's the modeling perspective of H, conditioned on that, what I will draw is one of the means, and then there is the variance, right? So the variance is just sigma square. So we were looking at spherical Gaussians and made even another simplifying assumption that they all have the same variance. Like all the components have the same variance, they can have different means, and we use the vector representation for this categorical variable. So the selection variable can take one of k choices if there are k mixture components, and we decided to represent it as a vector because this way both continuous and discrete random variables, we can just use the vector representation, right? So it's much more convenient. You can look at it as a linear system. There's a lot of nice properties that arise if you write it this way. And that's what we were concluding at the end of last class. So the selection variable can take one of k values if there are k mixture components. So I had this matrix A where each column represents one of the component means, right? So by H being a basis vector, it selects only one column at a time. So it selects only one of the mean vectors each time. And that was the right? So I could write my sample, right, my random variable from Gaussian mixture as this combination. Any questions here? Right, so when you have Gaussian mixture, it's a mixed random variable, right? There's both the discrete part of selection and then there is the continuous part, right? But this discrete part is hidden and that's why you don't know which component it's coming from. Yeah, and that's why it's also, we call it unsupervised learning because we don't have supervision on H. So far, so good? So yeah, so now I can ask what will PCA do here? Can't do PCA because we want the covariance matrix. So what will the mean look like?
Should just be a AH minus like mean. I guess.
What is the expectation of the first term?
The mean of means.
I mean, that's what is mean of means, right? I want to compute that.
But the the mean of like
Each one of these, right? So what is it mathematically in this equation? I can take the A outside,
yeah.
right? And that's why it's mean of means, right? What about the second term? 0, right? You don't have it. So it's, I mean, this is, I'm sure you. Okay, so that's the mean. We'll call it mu, I guess. So I can also compute now my variance. What would my covariance matrix look like? Yeah, so if you, right, so you can, I'll call it W. This is the vector of the component proportions, right? So each component has certain proportion, right, or the selection probability, I'll call it W. And then this is, this is also a vector, by the way. Right, because H and Z are uncorrelated. So when you look at expectation of H and Z, right, it'll be 0. sorry, there's the term that looks at, right, shifting this, right? So you have this x minus mu transpose and then zz transpose, that is the sigma square I. Yeah? So this is 1 through k. So what's the rank of this matrix? What is each term in the summation? What is the rank of each term in the summation? What is the rank?
1.
Right? Because it's just a vector transpose. So what's the sum of k components? What's the rank? So what's the catch? Is it rank k? Is it lower? What do you think?
Should be rank k.
These vectors, right? So the k vectors are of the form ai minus mu, right? This is my, I'm taking combinations of the rank 1. Is it the case? How did we define mu? Recall what we wrote there. If I write it as a summation, what is it?
So mu cancel out the rank k minus 1.
It's k minus 1, right? Do you see that? So that's a nuance, because it's easy to say, oh, there are k components, each one is. So what dimension of PCA should I be doing? I mean, the answer is there. Because if I do k, then we know it's only k minus 1 dimension, I'm going to introduce more noise. Right? So if I do I obtain? What does it give?
Should we test?
Still this noise term, right? So let's assume, I can estimate sigma square, by the way, by another trick. So we can first cancel it out. There's a simple trick to estimate sigma square. So I'll come to way to estimate sigma square. Assuming the data is truly drawn from this model, right? There's no impurities. What if I looked at a direction that is in the null space of this? What do I get? If I look to this matrix, it's only the noise, right? So I can estimate sigma square from all the other directions. And I'm making the assumption that it's simply identity. So in any direction, it'll be lower eigendirection than the top ones, right? So the top k minus 1 will involve the mean components. If I go to the ones below from this matrix, from my covariance, so I can subtract it out, right? Like, so I can look at PCA of my covariance matrix, let me call it M2. This is my second order moment. Or let me call it sigma. At sigma, so I can look at sigma minus the cancellation of the noise term. That I get only that subspace. So what do I get? What do I get from this?
You mean like you're reducing it to k minus 1 dimensions? Or so you're only doing like one PCA step?
No, you're doing k minus 1 rank PCA.
K minus 1 dimension. And they started out as D dimensional? Or
Yeah, I mean, this is the subspace, right? It's still in d dimensions, but you're looking at now k minus 1 eigenvector. Right, and then I can also look at my mean vector, right? I already have, I know this, so I can also. So this is the information I have. Right, so I can write this matrix as a, say mu, this big mu matrix is the same mu, right, on all the columns. Then it is diagonal with W, which is just mu repeated in every column. That's what I get. Right? So let me just make sure. So this is my big mu, which is mu, mu. Okay? This information. Do I know everything about the model if I know this? What do you think? What am I after in the first place? What was our goal?
Now we know the expectation of edge, but we don't know what the edge exactly is.
Right, so you don't have the information of what the selection variable is, right? And you also, I didn't know A, I didn't know sigma square. I've estimated sigma square. Have I estimated A? So I need to know A in order to infer what H is, right? Because otherwise I can't compute the probability, right? Because one approach is to say, I want to look at what is the posterior of what H is given X for each sample. And if I knew A, I can compute this, right? It's in fact a pretty easy computation, right? It's just like looking at each component, the probability H is the ith component, right? Or rather the Gaussian term, and then you normalize, right? So it's something simple, but to write it down, you need to know this mean components. Can we do this now? From PCA, we are getting this matrix. Can we get A from this?
Yes, because you just recenter the A minus mu. Just,
So from this, what do I have? I have, so okay, let me ask you one more question, right? Simpler question. Let's say I have a matrix B that I want to know. BB transpose. If I tell you what BB transpose is, can I tell you, is there a unique B?
Decomposition, something like that.
So I'm not even asking how, right? I'm asking identifiability. Is there a unique B
in the general case.
yeah, just any general. Why not?
For example, if B is unitary, BB transpose will be identity. Anything.
Exactly, right? So, or more generally, you can say you can always do this, right? You can always have like a unitary matrix, right? Actually rotating the coordinates, right? Or rather transforming, in this case, it's rotating the coordinates, right? You don't get the coordinates, right? Because this is any coordinate system, BB transpose would still be the same, right? You can rotate B and still obtain the same answer with BB transpose. Space in which A lives, right? But not the actual vectors. So meaning if I now have, like, say, these vectors, they'll live in some subspace, right? I'm getting that subspace. Vectors are, right? So I'm not completely done. But then, you know, I can still do dimensionality reduction, right? So I can reduce the dimension in which I'm doing the computation. So what is the popular method? You know, you've obviously seen yeah, k-means, and then if you are more sophisticated, you do EM, right? Which is nothing but soft k-means, right? In the k-means, because in each iteration, you have to decide only one of the clusters to which the sample belongs. You re-estimate the parameters of that cluster, right? Essentially, if you also want to estimate the variance, and you go back and forth. Right, so that's what EM is, right? You're going between inferring the selection. Right, so if you knew the selection variables, it's easy to fit each of the components. So you go going back and forth. And in the EM, it's just like the posterior, right? You're not completely assigned based on the probability it belongs to different clusters. Right, so people do that in practice. So can PCA be useful? Still want to use that method, how can PCA be useful? I'm sure you've seen this before.
You still get the subspace, right?
Exact, so this is called spectral clustering. Essentially this, right? You do PCA, you project onto the space in which the mean vectors lie, and then you do clustering in that lower dimensional. Can be really efficient because maybe there's good separation along this, right? The top components, right? Because and still tell them apart by clustering, right? So naturally, the first two moments by themselves cannot tell you everything about the distribution, right? So it's only for moments tell you about the distribution for continuous variable. So anything that's not Gaussian, you need more moments to characterize the distribution. generating function, which you probably did in your first probability class. If you recall moment generating function, right, what that gives is moments of all order, right? That's the exponential. And for a general distribution, you need all the infinite moments to characterize the distribution. But for special distributions, maybe just low order moments. Right? So for Gaussian, it's just the first two. So anything that's not Gaussian, you need higher order moments. So keep that in mind when we go to tensors. That's when we will ask, can that help me more? Right? So that's the use of tensors for looking at higher order moments of data. Okay? But here, okay, I'll still limit to first two moments, right? But I'll use that to compute this dimensionality reduction so that I can do spectral clustering in a lower dimension and be hopefully the cluster centers and being able to separate the clusters. So when does clustering fail? Yeah. There's a reason I drew samples that pick of the samples I drew. I mean, there I can tell which are the clusters, right? So that means they're separated. Clustering is great, right? I mean, kind of obvious, but a statement to be made. And that really depends on this noise, right? So how much everything gets mixed up, I cannot cluster, right? And it'll fail. So if you see any kind of guarantees on k-means and EM, right? So that's all. If you have separate clusters, so you don't have a lot of noise, this is great. But on the other hand, if noise dominates, this will completely fail, right? So clustering, many cases where you don't have separation and we can't do clustering. Okay, so that's a limitation of that method. So what did we learn? I think I made several points. Can someone try to recap them? Points. What was most interesting to you? Come on, I want some participation. I don't want to pick people to. Yeah.
Actually, I'm still a little confused. Can you write out like how we're recovering H from this like?
Oh, I haven't solved the problem, have I?
Oh, okay.
At least not through this. It cannot be recovered.
Okay, I learned that.
Right? Okay. So you can recover it if you do k-means or EM, right? You can always first do. If you do k-means or EM, I guess you know how to recover A, right? Because that's what the method does iteratively between alternating the estimation of H, right, and estimation. Yeah, so we still don't have a method of moment solution for recovering A. That's what tensors will give us, but I haven't come to that. Right, so the main takeaway is if you're still trying to do PCA on non-Gaussian data, it can help you in dimensionality reduction, at least in the case where, right, there are only useful if K is much, much less than D. Right, you have few components in high dimensions, you want to reduce dimension to just the, so you don't want to look at full dimensional space. That's when it's helpful. Okay, so, and that's the basis for spectral clustering, and people, do many variants of it. They can like relax the Gaussian assumption to some extent. They can, again with some caveats, they can also try to relax the spherical assumptions. There's all kinds of like further complexities you can build in, but this is the basic principle. Okay? And the other main takeaway I want you to keep in mind is this way to express both the categorical variable and continuous variable as vectors. Right? This is unusual because if you write probabilities of categorical variables, that's you kind of like write what is the probability it takes value, the first category, second category, so on, right? You just kind of write it out that way, you don't think of them as vectors. So I emphasize this because in many of the calculations we'll do on joint probability distributions on many, many variables, you need this kind of representation. Even if everything is discrete, thinking of them as vectors will make it much more convenient when it comes to spectral methods. Right? Because we want to ultimately operate on joint probability matrices or tensors, right? And that's much nicer to express if you write it in terms of categorical variables. Categorical variables as vectors. Okay, so that's the other main takeaway. So good, keep this in mind. Now we'll do another hidden variable model, right? So this is a hidden variable model, right? Because the selection variable is hidden. It was quite simple in the sense the only thing that was hidden was which Gaussian you're drawing from. So we'll now do a slightly more complicated distribution, and this is the hidden Markov model. How many of you have like seen it, worked with it? Good, quite a few, right? So the main idea is now you have this hidden random variable for each time step, right? Or each step in the sequence. So now the model, instead of just being one sample, it's a sequential model. So you take samples at every point in time. Right? And these are discrete time models, meaning the time is discrete, right? There are discrete time steps. So you have this model where it is now x1, x2, so on, up to even x infinity, right? These are the samples at each of the time steps. And the way we represent these samples is through hidden variables. So this is where we'll use the graphical model notation. How many of you are familiar with it? I'll give a recap in any case. Let me first write it out. Right, so can someone tell me the definition of the graphical model? Or in other words, what do the nodes and edges in this graph represent? So before I go to HMM, I can do the simpler version, right? Or a degenerate version of this is just a Markov chain. So what's a Markov chain? Sure, you've all seen Markov chains. right? What is the basis for defining Markov chains?
The next iteration's only dependent on the previous iteration.
Right, so how do you express the dependence formally?
The like probably distribution of x n plus 1 is given all the other kind of past samples is only equal to x, the probability distribution of x n plus 1 given x n.
So what that really tells you is conditional independence, right? That's the basis in terms of like saying what's dependent on what, right? So how would I represent the Markov chain in terms of the graphical notation? Just a chain, right? So what do the edges in this chain represent?
Transition probabilities.
Right, so and that's kind of like the values, right? So to begin with, even a simpler version is, it just gives you conditional independence, right? So if I'm conditioning on a node, that's equal to deleting that node, right? So I can condition on the node and then I can look at the, whatever, if there is still dependence between variables, there will still be an edge. Conditioning is equal to deleting. On the node, this part is completely independent of this part, right? Because there's no edges going around. But on the other hand, if there was some other edge like this, it's not conditionally independent, right? So that's a simple way to express conditional independence relations, because you can say that conditioning is equivalent to deleting the node in this graph, and if there are no edges going from certain nodes, you know those are conditionally independent. So here what we have in the hidden Markov model is the Markov chain on the hidden variables, right? You directly don't observe this Markov chain. What you observe is some transformation of that Markov chain, right? And that's why this is more difficult, because I don't observe these hidden transitions. So if it's just a Markov chain, how do I estimate the parameters of a Markov chain? What are the parameters I should be estimating? What describes a Markov chain?
Something like the transition.
Right, so there is the transition matrix, right? So this is like the P of x I plus 1 given, let's assume homogeneous, right? We'll do only homogeneous in all of this. And that's because, that's when you would have like concentration, right? You can compute across the chain. So I'll use this T for the transition probabilities. So what else? Is there some other parameter in the chain? There's the initial one, right? So pi is the initial probability. Okay? How can I estimate this in a Markov chain? I can look at empirical probabilities, right? So if it's homogeneous, I can even look at like transition probabilities all across the chain. Of course, there is the nuance that for concentration bounds, these are not IID variables, right? So I have to be careful. I have to think about mixing. There are some nuances. But roughly, the idea is there are empirical probabilities I can compute. So I can look at what my transition matrix is, right? So that's why it's straightforward, because I can directly observe these transitions. But here I cannot directly observe the transitions, right? So it's much harder for me to tell what is the transition matrix. Okay? So that's why kind of like, it's always good to go back to the simple case, right? What if it's observed and now what if it's not, right? And so just some notation here. We'll still use pi to be the probability of the initial probability, we'll still use that. We'll still use T to be the transition matrix, but on the hidden state. And still the homogeneous model. Maybe I'll use T here for time. So let's say this is Tij. I think this is I, this is J. Okay? We'll do discrete. This is all discrete random variables. Right? So both H and X are discrete in my setting. I mean, we can extend all of this, but for simplicity, let's do that. Okay, so let me just write down X, H are discrete. Okay, this is my transition matrix. What else do I need here?
Hidden state to observation.
Exactly, right? So I need the conditional probability of the observed given the hidden, right? On the same time step. So again, I'll call this matrix O just because, it's the observation matrix, and this is. And again, it's the same, it's all discrete, so I can look at the probabilities this way. Okay, this is the observation matrix. Right? This completely describes the hidden Markov model, a homogeneous hidden Markov model. So if I can estimate all of this, then I'm done. So how should I go about estimating the parameters? What would you do? I give you data from this homogeneous HM. Right? Tell me how I can fit this distribution. What is the standard approach? We just talked about standard approaches, right, for Gaussian mixtures.
Solve in a linear system.
Right, so can do this, but if it's just a standard latent variable model, what would you do? You'll do EM, right? So you can always do EM, right? It's just that it's even more complicated here compared to Gaussian mixtures. And that's called the forward-backward algorithm. So I won't write down the equation details, but you can imagine that you kind of like go forward and backward, infer the hidden states, right, and then refit the parameters. So you can do that approach. But then this is even harder than compared to Gaussian mixtures. So there is no convergence guarantees, right? So you don't know if you're inferring the right hidden states, what's happening, no idea. Because essentially what you're trying to do is do maximum likelihood estimation, but it's a non-convex problem, and there are no guarantees of what solution we'll find. So that's what people do, in any model, right? They try EM. But now we can ask, okay, are there alternatives, right? So one is this perspective of dynamical systems. So if you're a control person, if you're, had that background, you could say, what does the spectrum look like? How can I think of this from the operator view? So I think that's much more natural to people who are coming from that background. So that's what we want to do. And so what is the intuition here in terms of, trying to apply what we had here to hidden Markov models? Right? There's a reason after mixture of Gaussians and PCA, I'm using this example. So what do you think we should even be looking at? Where do we start? So what did we do here? We started looking at the moments, right? So first we computed what is the mean, then we looked at covariance matrix, we tried to reason about the eigenspectrum there. How can I apply spectral methods here? What does moments mean in this case? What is the notion of moments for a categorical or discrete random variable? How can I think about moments? If it's just one categorical variable, what is the moment? I mean, I can look at even for this age here, right, that was a categorical random variable. We did say expectation of age was W, right? This notation. Now I can ask the second order moment. What is this equal to? What are the values that age takes?
0 and 1.
No. Going back to this example. It's taking k values. Right? I'm going back to this example. So I don't know where 0 and 1 come from. I mean, the Bernoulli is a special case. But recall I'm doing this vector representation now. Right? So we won't look at it as 0 and 1. So how can I compute this? I can compute this.
Would be the identity K, the line identity with K, frank K.
We have to be a bit more careful, right? What's missing there? So it takes all these values, but what is the probability it takes each of the values? So let's write it out. Right? So one of the values it takes is EI. It will also be EI transpose, but what's the probability with which it takes this value?
WI.
WI, right? What is this matrix? Linear algebra. Can I simplify this? How can I write it compactly?
Diagonal.
Yes, sir, exactly. Is it giving me more information? Compared to the first order moment? No, right? Well, if I went to third order moment, would it give me more information? So for a discrete random variable, all you have is first order moment, right? There is no other information in higher order moment. So you can't just, we are dealing with discrete random variables here, so I can't just compute higher order moments of one random variable. But I have more here, right? What is the additional information I have? There isn't a single random variable, right? I have infinite, in fact, set of random variables. So what can I do in that case? The joint probabilities, right? So I don't have to now look at the empirical distribution of one random variable. What gives me information is now joint empirical distribution of many random variables together. And that's what will tell us these conditional independence and these kind of dependencies between them, right? And we can compute it. I mean, between the observed random variables, I can always look at my joint distribution. Okay? And this is discrete, I just look at the counts, the joint counts, right? So that's what is the notion of method of moments here, right? In mixture of Gaussians, the resulting random variable is still continuous, right? I can just kind of start with the mean, variance. We'll even do the third order moment when we look at tensors, right? I can keep going that way even with just a single random variable. Many draws from that single random variable. But here, this is a different setup because if you just look at one random variable, all the information is just the first order moment because it's discrete. But now if you look at joint random variables, right, you can express them as matrices, tensors, and more. It will still be the first order moment but with multiple variables. So that's what will help us think about the spectral methods. Okay? So what we'll be operating is, in terms of the spectrum, of the joint distribution, right? So you can look at now joint distribution of variables and look at spectral decomposition. Does that make sense? No? You have a question? Sure.
No, just what you say is a very high level
Yes.
summary.
And now we'll go. So I want to always give that high level picture of what's to come, right? I don't want to keep you in suspense. Okay? Hopefully that makes it easier to follow through and why we'll do all the math. So now we'll go into those details. Yeah, so that means the next natural thing to do is to ask how can I write down my distributions, right? How do I express my distributions in a clean way? And we'll have this notion of observable operator. So I want to first define that, and then we will use that to write down these distributions compactly. So again, what is the intuition? The main intuition is, right, if I look at joint distribution between x1 and x2, it's going through h1 and h2. Right? I can, if you recall the conditioning trick, I can condition and then take the expectation. And if I do conditioning, I have this conditional independence, right, between x1 and x2. For instance, the one relation is x1 is conditionally independent of x2. If I condition on, right, h1 or h2, any of those, right, let's say h2. Right? I have these relationships, and this is the notation I use for conditional independence. So the intuition is, because I have this conditional independence, if I want to express my joint distribution between x1 and x2, I can first look at conditioning, right, and then this essentially becomes a product of the matrices, right, something that involves O, something that involves T, right, so that's kind of the idea that you kind of can break down this joint distribution in terms of the observation matrix and the transition matrix. Okay? And that's what will help us reason about the spectrum of what the joint distribution of x1 and x2 looks like. And again, we'll make the assumption that the hidden dimensionality is much smaller than the observed dimensionality. In this case, the dimensionality means the number of categories, right? So the number of hidden states is much smaller than number of observed states. Right? I mean, that's when the spectrum is meaningful. Otherwise, it's full rank, right? You don't get any of the nice low rank assumptions. But in many big data problems, that is the case, right? You have very high dimensional, time series that you see. You hope that there is some low dimensional way to explain that. Okay, so that's the regime in which we operate all these spectral methods. It's for high dimensional data. Okay? So now let me define this parameter first, and then you'll see in a minute why this is useful. We call this the observable operator. I think this goes all the way back to 61. So I think some of the control people did this first. So the credit does go to them. Right? So that is indeed like a mixing from many fields. So I'll define this matrix AX, which is nothing but a condition on the hidden state at some point in time. Okay? And I want to look at, so if a condition on the hidden state, let's say here, right? So a condition on H3, right? Then I want to look at the observation at that same time as well as the hidden state at the next time step. Right? So I'm looking at HT plus 1. And I'm looking at XT. So I'm looking at the joint distribution matrix, but conditioned on a certain hidden state. Right, so this is just a definition here. The dependence on X, I'll write that this is equal to X here. So I'm just looking at a certain probability of only certain observed state. Okay, so that's this x here. And then I can go through all the hidden state values here, all the hidden state values for the next state. And that's why this is a matrix. Okay, so what this says is Ax of I comma j is nothing but probability of ht plus 1 equals I. Xt, I'll keep it fixed at x. Ht equal to j. Okay? This is a matrix I'm defining. So what's the conditional relationship, conditional independence relationship between these three variables? It's there from the figure, right? Which two are conditionally independent given the other? I have three random variables. What's the conditional independence relationship? Remember, I have the figure there.
xt and ht plus 1.
Right? Are conditionally independent given ht. Right? So how can I write this probability? What is the value of this probability given these parameters t and o? T and O are matrices.
Shouldn't this be a Tij times Lj?
Exactly. Right? So these two are product distributions, right? So it's just conditioned on each one separately, and that's nothing but equal to Tij times. Okay. By the way, if you take two matrices and multiply them along the columns, right? Take the vector products along the columns. That's called Capri-Rao product. I won't, use that again, but I will just kind of put that here because this is very convenient to express other kinds of conditional independence properties, and you want to do this operation. So, I will not use this here, so let me not formally define it. But just note that if I'm taking, what I'm doing here is taking the same column in both these matrices, right? And then I'm doing, here it's x, right? So I'm looking at the cross product between them, right? So if you recall like Kronecker making a product and all this, that's in terms of cross products or vector products. If you recall your dot product versus vector product class, you can use that here, but we won't need it. So that's why I'm just quickly referring to it, but we won't need that notation. But that's the operation being done here, right, just as an aside. But you don't have to worry about it. Right? The main thing to keep in mind is because this conditional independence, I can break down this probability, right? I can write it in terms of these product of these matrices. Okay? So what was the dimension of this A matrix? If there are, I think here in the notes, the notation was M and M, so I will just go with, so this was M states, this was N states. Okay, so this is a M by M matrix, right? Because this X is fixed. I'm not running through different X. Okay, so this is M by M matrix. And then, anyway, this one is just, right, X is fixed here, so all the dimensions work out. Okay, just as. So we call this the observable operator. Right, so now if I want to look at, but then I don't have access to this operator because I don't know the hidden states, right? I don't get samples from my hidden states. So I can't compute the empirical distribution there, right? So that's why we want to think about the observed distributions. right? So I can ask what is my joint distribution between the first two variables. So this is where I can do the conditioning trick, right? I can condition on H1, I can condition on H2, and you can imagine now that is because of the conditional independence, I have breakdown of the matrices. So I won't go through all the steps. You can do that in your own time, but I will write down that this is the claim. So we'll have AX2. This is the probability that the random variable x2 took value x2, right? So I'm kind of slightly abusing the notation here. Same with x1. So recall pi was the marginal probability of x1, and we have the all ones matrix here. So this is nothing but the probability that the value was x1 and x2. So this is scalar. Right, the first time step had the value x1, the next time step had the value x2. Right, so this is scalar. So this is the claim. I didn't derive the claim, but you can do that by conditioning and looking at each of the conditional distributions. And you can imagine that it because this kind of operator will come up because it involves the hidden states. Okay, so what this is telling us is, if I want to write down the joint distribution of these two random variables, all I need is pi and then these observable operators. So this is an alternate explanation for my observed data, right? Here you see I'm no longer writing it in terms of T and O, right? That's hidden in this expression. But I could directly try to aim to estimate AX here. So if I knew AX, I can still fit my observed distribution. Okay, and that's in fact the case for any series of distributions. In fact, if you have say T time steps here, all you do is chaining of all these T matrices. Right? You just go AX1, AX2, so on. Okay, and so that's why this is an equivalent explanation. Right? So if all you want to do is predict what is the value at the next time step, the value of the observed distribution in the next time step, you don't need T and O. You can do this if you knew what AX was. Do you see that? Because I can express all my joint probabilities in terms of AX and pi. Right, of course, we also need to know pi. Okay? So this is true in general. So I have if I had more values here, I would also have just more of these matrices. Right, and because it's homogeneous, it's the same, right? If I knew AX for all x, I'm done. Right, that's the set of matrices I need to learn.
What's the effect of the ones column? Or
So the one row, what it's really doing is summing up, right? So it's think of this as marginalization over the hidden variable. Right, that's what the ones is kind of accomplishing. So that comes up when you write out the expressions. Was that your question too? Yeah. Okay, so believe me, this explanation, it requires a few steps, but it's really just the conditioning rule and using the fact that they're conditional independence relationships. Okay? So that's why this is called an observable operator, because I can just use these matrices AX and explain my observations in a HMI. Right? So if I can estimate just these AX parameters, I can now predict what my next step observation will be. Right? I can write down that probability. Right? So I can write down the marginal probability. I can also write down the conditional probability. Right? I've so far observed a sequence of data. I want to ask what is my next time step going to look like. Right? That's forecasting problem. I want to forecast what will happen in the future. And if I want to do this, I can use these observable representation. Right? I don't need these original matrices T and O. transition and observation matrix. On the other hand, if I want to predict what the hidden state is, this doesn't give me that. Right? I have to then get to my transition matrix. Okay? So this one is only good for prediction. Right? If I want to predict something about my observed data, I'm giving you an equivalent representation. But if you want to actually infer about the hidden states, this doesn't give you that. Okay, so this is what was the joint distribution. Right now the question is, how do I get these AX? Right? So can I get these AX? And if not, why not? That'll be the next question. Any questions so far? Let me just do this here.
So for A, there is no information about hidden states, right?
I mean, it's implicitly there, right? Because it's product of these T and O matrices,
Right.
but they're mixed up together, so you don't get T and O separately, even if you estimate AX.
So what is the difference between just getting the probability, condition probability of observables? Like is it with this expression? What
So
is
it
the
depends on your goal, right? So if your goal is only to predict on the observed data, say like forecasting, you can do that without caring about what T and O individually is, right? Because I don't want to reason anything about my hidden states. On the other hand, if the goal is to discover the hidden states, right, then we need to try to estimate this, right? This observable operator will not do. So there's a reason this came up in control, because in control, what do we care about? We care about controlling, right, our observed states, whether it is position, velocity, and so on. Right, so I don't care what is the hidden representation. On the other hand, let's say in genetics, right, or in other kinds of biological systems, I want to infer this hidden state because that tells me about the underlying mechanism. Right, so that is, discovery problem, this is a prediction problem. Right, so it depends on your goal. But here we are assuming the goal is just to predict on the observed space, so I can use these observable operators. Okay, is the distinction clear? And in the next class, when we do tensors, we'll talk about the discovery problem, because in this current one we cannot disentangle T and O, but if you have tensors, you can actually do that. Yeah, so that's the power of tensors. One of the superpowers. So yeah, so let me write out a few more expressions, and then I can kind of like explain what that is happening. Right, so let me introduce some notation. So I'm going to like write this matrix P1, this probability of just x1. By the way, by looking at probability, just in right counts of x1, I can estimate what pi is. Right, so I can know that. So I don't, of course with finite data that's concentration bound, but I can estimate that. So I'm going to write this as, this is just a vector, but in the other case it will be matrices. So don't worry about the actual expressions. I will describe what the intuitions are here. That's more important. So what did I do here? I looked at the distribution of the first three measurements. Right? So the joint probability of all three is here. This is just the joint probability of two of them, and this is just the marginal probability of the first distribution. So I'm kind of sequentially growing. I start with the first random variable, I look at first two, I look at first three. Right. So if it's two discrete random variables, I can express their joint probability as a matrix. If it's three random variables, I can't express it as a matrix, right? So I need a tensor. But pretend in this class you don't know tensors, right? And probably you don't know tensors. So we still want to do matrices, and that's why we'll take a slice. Meaning we'll always fix this second random variable to be x, right? And just vary the values that the other two random variables take. So that's why it's still a matrix, right? So here I'm varying the third and the first random variable, looking at all the values they're taking, and looking at the joint distribution, but fixing the second random variable. Okay? So at this point, these are just matrices, but you can think of them as now moments, right? That was the analogy I was talking about here. You know, I can't do for a single random variable, I can't look at higher order moments, but I have more random variables here. So I can start with one random variable, I can go to two random variables, three random variables. That's the analogy of higher order moments, by which I can get more and more information, right, in this HMM system. Any questions? So the main claim is, I mean, of course, right, so these distributions, you know, I have it in this form of observable operators, right? I already told you this is true for any set of, any sequence of observed distribution. So the main trick here of the spectral method is, right, that, you know, this is, by the way, here, what is the dimension of this matrix? 2, 1. What is the dimension? It's the number of observed states, right? And that's n in my notation here. So it's n by n, right? This is n by n matrix. This is like a n-length vector. This is also n by n. So this is a n by n matrix, but what is its actual rank? If I'm asking the question, it would be low rank, right? What is its rank?
Empire?
Yeah, so the rank is m,
Okay.
right? At most m, right? Assuming m is smaller than n, right? That's our assumption. As I said, all this high dimensional setting is where n is much, much bigger than n, right? That's what we are assuming. So the rank is at most m. So when is the rank actually equal to m? What assumption do we need for that? I mean, roughly the assumption you need is with respect to these matrices, right? Because you can always do like a trivial case. You can, you know, say that the same hidden state, you just copy it and call it another state. That's a degenerate system, right? So you don't want that kind of degeneracy to happen. And that's expressed through the rank of the matrix T and the rank of matrix O, right? Or another setting is where two hidden states always cause the same observations, right? There's no change in that distribution. So there the matrix O would be rank deficient, right? So you assume matrix T is ranking, or rank, sorry, M matrix, it's full rank. Right, so and that also relates to ergodicity, if you recall, like the Markov chain. Right? So everything kind of goes to everything. Okay, so that's the assumption of the rank here. With O, what is, you know, this is now a rectangular matrix. It's not a square matrix, right? It's a tall, thin matrix because you have many, many observed states. You have only few hidden states. Okay, so it's n by a matrix. So we want this to be full column rank. Okay. And that also means the different hidden states give rise to different kind of observations here. Otherwise, you can't easily distinguish what the hidden states are. I mean, it's not impossible, right? There could be still approaches that would still try to work without these assumptions, but these are sufficient assumptions. Okay? So that's the idea that, this will be, the matrix AX will be rank M if these two are rank M as well. Right? Because you're just taking that together. Okay, and hence, in that case, even these will be rank M. So that's why the spectral methods have a place here. Right? Like you have these large matrices which are low rank. So the natural thing I will do is do SVD, right, or do eigendecomposition. In this case, it's SVD because it's not symmetric. Right? I'm not dealing with symmetric matrices. When it was the moment of the same random variable, that's symmetric. Right? So we'll do SVD here, and then we'll use essentially the projection to that lower dimensional subspace and do the operations there. And that's the basic principle. I'll just maybe conclude in the next class since we are almost out of time. But the main idea is if I do SVD on these matrices, I get dimensionality reduction. And I can still go with a change of coordinates of my observable operator, but I can still aim to fit my observed distribution. So that's what we'll conclude in the next class. Thank you.